Greetings! Good day everyone! In this video, I will be discussing about multiple regression. Introduction. So when we talk about multiple regression, a multiple regression is a way to see how one result dependent variable is affected by two or more things like independent variables. It helps us understand how different factors work together to influence one outcome. For example, if you're trying to predict someone's weight, the dependent variable, then you might look at their height, age, and exercise level as the independent variables. So let's move on to the main discussion. So here, I will be answering these questions based on this partial output for multiple regression coefficients. The regression analysis is to predict sale price based on house size, number of bedrooms, age of the house, and distance from the city score. Since we have four independent variables or predictors here, the multiple regression model could be written as follows. It could also be written in this form based on the definition of the x variables here. Beta 0 is the constant whose estimate is referred to as intercept here, and the beta 1 to beta 4 are the population regression coefficients or parameters for the four independent variables. They are also sometimes referred to as population slopes. This epsilon here is called the error term or error variable. It is sometimes represented by u. It accounts for the variability in the dependent variable y that is not explained by the regression model. The values of beta are not usually known but are estimated from sample data as we have here. The estimated model or equation is therefore presented as follows with the coefficients taken from the first column of the output here. Note that the dependent variable now has a hat to indicate that it is estimated or predicted, and the error variable is removed since this is an estimate. Now, the estimate of the model's constant is 565.3. Is the expected value of y or price when all independent variables are zeros. In this scenario, it does not make sense for house size and number of rooms to be zeros. Therefore, the intercept has no practical meaning or does not make sense. Next, we interpret the coefficients for two of the variables. For house size, the estimated regression coefficients represented as beta hat 1 or b1 with a value of 0.113. It means for every square foot increase in house size, sale price increases on average by about $113. That is because sale price is in thousands, we have to multiply by the 0.113 by 1000 to obtain the $113. And in contrast to simple regression, we usually add holding other variables constant in multiple regression. This means that this per square foot increase in expected price is for homes with the same number of rooms, same age, and same distance. Similarly, for distance, the regression coefficient is negative 15.975. It means for every additional mile, price decreases on average by about $16,000. Holding other variables constant. Next, we construct a 95% confidence interval for the age coefficient. Typically, confidence intervals for the coefficients are included in regression software outputs. Nonetheless, to calculate them, the formula is given as the estimated coefficient plus or minus the t critical value times the standard error of the coefficient. With 95% confidence, alpha is 1 minus 0.95, which gives 0.05. Recall that the number of observations n equals 34 and the number of independent variables here is k equals 4. Thus, the degrees of freedom n minus k minus 1 equals 29. Since confidence intervals are always two-tailed, we divide alpha by 2 to have 0.025 in each tail. With df equals 29, the t critical value is 2.045. So, for age, the coefficient is 1.3849 plus or minus the critical value times the standard error for age. That is we are 95% confident that the true regression coefficient for age lies between negative 3.8 and 6.5. Next, we estimate the sale price of a house with this given information. Here again is the estimated regression equation. We want to point predict sales for this house by substituting the values in the equation. The house size is 1,900 square feet and there are 3 rooms. It is 96 months old, but note that age is in years and not months. So convert the 96 months to years by dividing by 12 and that gives 8 years. The distance is in miles, so we simply enter 20 here and that is approximately 780. Since price is in thousands dollars, this is $780,000. Next, we move on to testing the significance of each regression coefficient. For each independent variable xi, the null hypothesis will be that the regression coefficient is equal to 0, that is not significant. And the alternative will be that beta I is not equal to 0, meaning the coefficient is significant in the model. That is, the corresponding x variable is linearly related to y. We are testing this at alpha equals to 0.05. As we saw earlier, the degrees of freedom is 29 and the two-tailed critical value is 2.045. In essence, we will reject the null hypothesis if the t-statistic is less than negative 2.045 or greater than positive 2.045. In other words, if the absolute value of t is greater than 2.045, we reject the null hypothesis. Note that the t-stat here is calculated as coefficient divided by standard error. Also note that since our output here contains p-values, we really do not need to use the critical region approach. We could simply use the p-value rule. That is, we reject the null hypothesis or the result is significant if the p-value is less than our alpha of 0.05. Now, for the first independent variable, house size defined as x1 here, we will use beta 1 in the hypothesis. The test statistic is 3.444, which is greater than 2.045. So we reject the null hypothesis and conclude that the parameter for house size is significant in the model, or we have enough evidence to conclude that house size is linearly related to price. You can also see that the p-value is less than our alpha of 0.05, which corroborates our decision to reject the null hypothesis. For number of rooms, represented by x2, the parameter is beta 2. The test statistic is 6.268, which is greater than 2.045. So we reject the null hypothesis. The p-value here is 7.66 times 10 to the power of negative 7, which confirms our decision. So, we also have enough evidence to conclude that the number of bedrooms is linearly related to price. Next, for age, with parameter beta 3, the t-stat is 0.535, which is not greater than 2.045. So we fail to reject the null hypothesis. The p-value is also greater than 0.05 to confirm that. So, we conclude that age is not significant in predicting price. Therefore, we could drop age from the model for distance. Suppose we decide to test if price decreases as distance increases. We will need a one-tailed test, that is a lower-tailed or left-tailed test, because price decreasing as distance increases indicates a negative relationship. The alternative hypothesis will therefore be that beta 4 is less than 0. At alpha equals to 0.05 and degrees of freedom equals to 29, the one-tailed t-critical value is 1.699. And since this is a left-tailed test, the left-tailed critical value will be negative 1.699. The t-statistic is negative 8.355, which is less than negative 1.699. Note that the p-value here is a two-tailed p-value. So for this one-tailed test, we divide the p-value by 2 either way the p-value is less than 0.05. We therefore reject the null hypothesis, and we have overwhelming evidence to conclude that price decreases as distance increases. So these are the examples of real-world application of multiple regression. So the first is house price prediction. This is real estate companies and apps like Zillow use multiple regression to estimate housing prices based on property features. So the dependent variable is house price, and independent variable is size, number of bedrooms, location, age, proximity to schools, etc. The second is marketing and sales forecasting. This helps companies forecast future sales and understand which marketing activities have the biggest impact. So the dependent variable here is sales or revenue. And for independent variable is ad spending, seasonality, pricing, competitor activity, and promotions. The third is insurance premium calculations. Insurers use regression to calculate fair premiums based on risk factors. So the dependent variable is insurance premium amount. And for independent variables is age, health status, occupation, location, driving record for auto, and etc. The fourth is healthcare analytics. Predicting outcomes and optimizing treatment plans, cost forecasting, and resource allocation. So for dependent variable here is patient outcome, hospital readmission rate, healthcare cost, etc. And for independent variables are age, gender, pre-existing conditions, treatment type, and lifestyle. Lastly is education. Identify which factors influence student success and improve education policy and resource distribution. So for dependent variable here is students' performance, GPA, and test scores. And for independent variables is attendance, socioeconomic status, parental education, hours studied, and school funding. So here we are in the sample application for multiple regression. The image shown is a code that utilizes the Fleet GUI framework. So this section displays the libraries that I've used. So here I've created a sample data with features like size, rooms, distance, age, and price. So the target is to predict a price. This code X is the input data for size, rooms, distance, and age, and Y is the output price. This line shows to splits the data, so 80% is for training and 20% is for testing the model. Then this line shows a linear regression model is created and trained using the training data. This line of code is a setup for a page and input boxes where the user enters the house details. This line shows the result predicted price in the chart. This line of code is a function that runs when the user clicks the predict price button. Then after clicking it, it displays predicted sale price and visualization image. This part arrange input fields and plot side by side using row. The last important line that runs the app by calling the main function as the entry point. So the output explains that it has 4 indicated text fields and 1 button for predicting price. After you input in the text fields and click predict price, it shows the predicted sale price, which is the money, and the prediction plot, which is the visualization image. In conclusion, multiple regression is a powerful statistical technique used to examine the relationship between one dependent variable and 2 or more independent variables. It allows researchers and analysts to understand how multiple factors simultaneously influence an outcome and to make more accurate predictions. By quantifying the impact of each predictor while controlling for others, multiple regression provides deeper insights than simple linear regression. However, careful attention must be paid to assumptions like linearity, independence, multicollinearity, and homozydicity to ensure valid results. When properly applied, multiple regression is an essential tool in data analysis across various fields, such as house price prediction, marketing and sales forecasting, insurance premium calculations, healthcare analytics, and education. And that's all for today's video, and thanks for watching.